Alright, so in this video we're going to talk about polar form of complex numbers. Now before we go to that, we have to note that there are three basic forms of representing complex numbers. The first form is the general form. The second is the polar form. And the third is the exponential form. So in this video, we're going to concentrate on conversion from the general form to the polar form. Now, the general form looks like this. If you have complex number z is equal to a plus bi. This is the format for the general form of complex numbers, where a stands for the real part of the complex number, the real part, that's the side without imaginary I, understand? The side without the imaginary number I. While b stands for the imaginary part, that is the side with the imaginary number I. Now for the polar form of a complex number has this format: r cos theta plus ri sine theta. So we're going to learn how to convert from this form to this form. Now, in order to convert complex number, we have to look for two things. We have to look for the polar coordinates, and the polar coordinates are right there in the formula. We have to look for r and theta. So r and theta are called the polar coordinates. So the polar and r stands for the modulus or absolute value. And theta stands for the augment or the amplitude. So once we can get these polar coordinates, then we are good to go. Just plug it into the formula and you get your complex number in its polar form. So when it comes to the augment theta, some things we need to understand. Theta is the augment. Now theta can be defined as the angle theta is the angle which the modulus makes to the positive x-axis. I'm going to explain. Now remember your graph. If you have to draw a graph, and you have, let's say you have plotted your graph. Notice that this is your positive y, this is your positive x, this is your negative x, and this is your negative y, right? Now you have to, let's take an instance where you plot your graph and you have a straight line from here. Now assume now this line, this your plotted line, is the modulus, which is r. It's all going to make sense when we start solving. Now the augment is just the angle between positive x and r. So you're going to start with you're going to start drawing from positive x-axis, and you're going to move in an anti-clockwise direction. That's this way. So we're going to draw. Now for this kind of example, the augment is simply just going to be this way. This is going to be your augment this way. So this is your augment theta. This is for case 1, because you're going to have various cases where when you plot your graph, maybe it's going to lie in this quadrant, or this quadrant. So this is for a particular case. Now let's say we have a case where the modulus rests in this quadrant between the positive y and the negative x. This is meant to be a straight line. Okay, now in order to draw our augment here, remember we said the augment is between r and positive x. So this is r and the positive x. So we're always starting from the positive x and we're going towards r in an anti-clockwise direction. So we're going to start from here and we're going to move until we get to r. So this whole movement here is our augment. So let's take another case. Okay, this is moving outward. Let's take another case where we would have it in another quadrant. So yeah, if we have r in this quadrant, our augment, this is r, moving outward, this is r. To draw our augment, you can move from this point. Remember, you're going upward in an anti-clockwise direction. You can't draw from down, you must draw from up. So we're going to draw starting from this point and we're going to move until we get to r. So this becomes our augment. If we have another case where the augment falls in this quadrant, the fourth quadrant, you're going to have this way outward. Then your augment cannot be drawn this way. You must start from x and you must move upward and move in an anti-clockwise direction. So this is your augment. Now there are special cases where the augments lie on the same plane with one of these axes. What I mean is, I'm sorry, not the augment. There are some cases where the modulus rests on one of these planes. Let's take an instance. Let's say we have the modulus directly on this line. It's very obvious that your augment will just be this, which is theta will be equal to 90 degrees. Let's take another case where a special case where the modulus rests on the negative axis of x. So this is obvious that theta is going to be, you draw it from here and you move until you get to r. Mind you, this is r. Theta is going to be 180 degrees. Now we have another case where r rests on the same plane with the negative y. When we start solving some examples, all this will make sense. This is just like the basics, so that when we start making use of it, we won't get confused. So we start from the positive x as usual, move till we get to r. And this is theta. Theta is equal to 270 degrees. Now a special case again where the modulus rests on the positive x directly. So we can have this. This is your R. In this case, someone can say that there is no angle between the both of them. Someone can say that the argument is equal to 0 degrees. That's correct. Another person can decide to go all the way around, start from X, move to get to X. The person can say theta is equal to 360 degrees. This is still valid. Either this or this, both of them are valid. So we're going to take some examples to try to understand this properly. So let's take the first example. We have 2 plus 2 root 3i. Now the first step is to assign your x and y. Now let's say the real part should be x. That's the side without I is the real part. And the imaginary part should be y. So 2 root 3. There's no need to include the I, mind you. Now the first thing, remember we're going to look for the polar coordinates r and theta. R and theta. So we're going to look for r first. Now r is denoted by the formula the square root of x squared plus y squared. Now if you solve this, you're going to have the square root of plus y squared. If you solve this, you're going to have the square root of 2 squared plus 2 root 3 all squared. Now r is going to give you the square root of 4 plus, when you solve this, you're going to have 12. Now this gives you the square root of 16, which gives you 4. So our absolute value is 4. So we're done with this. Now we'll go over to this. We're going to do the same thing we did just a few minutes ago. We're going to try to plot a graph. Now plotting this graph, remember this is your positive y, this is your positive x, this is your negative x, and this is your negative y. Now you can see that this is the value of x and this is the value of y. So we're plotting this like on a graph, you understand? The proportion doesn't matter, just the placement of x and y. So x is positive here, so it's obviously not going to be on the left hand side, it's going to be on the right hand side. So this is, let's assume any random place, say this is 2. Now we go over to this, y is positive, so it's not going to be on the downside, it's going to be on the upside. So pick any random place. Remember I said the proportion doesn't matter, just the placement. So this is going to be 2 root 3. We're going to trace this just like a usual graph. Trace this downward, and where they meet, you join it. You draw out your R. This is your R. Yeah. Okay, this is your R. So remember what we said. We established a fact that to look for the argument, you always start with the positive x and you move towards R in an anti-clockwise direction. So you're going to move in this format, or in this way. So this is your theta. So now we can see that we have kind of like a triangle. We have kind of like a right angle triangle. So let's quickly erase this. Yeah, we found r to be 4. So we can quickly just like draw out this right angle triangle. So it's going to look like this, 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 and this. Yeah, so this is our right angle triangle, and drawing from this point, you understand. And we also established the fact that this is your theta. Establish the fact that this is your theta. We said this is r, obviously from the diagram. In order to assign values to this right angle triangle, remember this when you're plotting a graph, the middle part is your origin. Remember, don't forget. So if this is 0 and this is 2, it means the distance between 0 and 2 is 2. So this place is 2. If this is 0 and this is 2 root 3, the distance between this place is 2 root 3. And if the distance between these 2 points is 2 root 3, this is kind of like a rectangle. If this place is 2 root 3, this place also has to be 2 root 3. So we're going to have 2 root 3. So we're going to solve this. So we're going to have, we can use tan. Tan theta gives you opposite over adjacent. Now your opposite is the side facing the angle. So this is automatically your opposite. So tan theta gives you your opposite 2 root 3. All over your adjacent is the side that where the angle and where two angles are resting on. So we have 2. This is going to cancel out this. So you can see that tan theta gives you the square root of 3. So theta is going to be the tan inverse of square root of 3. And this gives you 60 degrees. This is a special angle. So at the end of the day, what you have to do is remember your formula for polar form of complex numbers. So you're just going to plug in your values of theta and r. So polar form is going to be z equal to 4 cos 60 degrees plus 4i sine 60 degrees. Now this is basically your polar form of complex numbers. You don't need to go for that. You stop here. Or you can factorize out 4. You can have 4 into bracket cos 60 degrees plus I sine 60 degrees. So this is your polar form of complex number. Now to verify if you're correct, you can easily just press this in a calculator. It's going to give you 2. You can press the first value in a calculator. It's going to give you the first value from the question. So 4 cos 60 gives you 2, and 4 sine 60i gives you 2 root 3i. So it's very easy. If you use a calculator on this and you're not getting your original question, it means there's a mistake along the way. So we go to example number 2. Example number 2 says we should look for the polar form of the complex number minus 5 plus 5i. So we repeat the same process. X is equal to negative 5. Y is equal to 5. Look for r. R gives us the square root of negative 5 all squared plus 5 all squared. This gives us square root of... Now, whenever you have an even power, the even power will make this negative sign disappear. But whenever you have an odd power, the sign will remain. So this is going to be 25 plus 25. This gives you the square root of 50. Translating this to solid form, you have we're going to have 5 root 2. We're done with r. Now we'll go for the argument theta. As usual, we're going to try to kind of like plot a graph. So we're going to have something like this. We're going to have something like this. And okay, let's plot it on a new scale so that it will look very big and explanatory. So we're going to have something like this and like this and like this. So if you're meant to plot, remember we said that our x is -5 and our y is 5. So this is your positive x, this is your positive y, this is your negative x, and this is your this is your positive y, this is your negative y, this is your positive x, and this is your negative x. This is your negative x. Now if you're meant to plot this on a graph, this is what's going to happen. This was going to happen. Now your x will definitely not be on the right hand side anymore because it's negative. So it will be here. To choose any random point. Let's say this is it. You say 5. Now for your y is going to be on the upside because it's positive. So you can choose any random point. This is 5. Now we're going to draw this. Just connect the both of them. Draw your r. This is your r. Now remember what we said. We said something about okay, this is -5. Now there's something you need to know, that when you're trying to draw this on your plane, your graph plane, when you get to the negative part, you don't need to indicate the negative sign. Understand? You don't need to indicate the negative sign. Just the placement is okay. There's no need to write -5 here. Just write 5. For the fact that it's in the negative side of x, we know that it's -5. So your argument, as usual, will start from the positive x and move towards this way. So we'll go like this and we stop once we get to r. So this is your argument theta. But now you can observe something, that this is the kind of idea we're going to apply here. We know that from this point, starting from this point down to this point, that's this little segment here, is 90 degrees. But we don't know this remaining portion. So what we're going to kind of like do is to try to look for the angle here, then add it to 90 degrees. So we can call this okay, let's quickly draw this in a bigger fashion. So if this is your theta, what we can kind of like do is to look for this small portion. You can call this place alpha instead. So what we're going to do is we're going to draw out this triangle here so that we can get alpha. So now drawing out the triangle, you're going to have this, this, and this. So this is, now remember that I said the origin is always here. So the distance from here to here is obviously 5. It's going to be the same with up here. So you're going to have 5. Now for this also, you're going to have 5. Now remember we said let this small angle here be equal to alpha, so that we can easily calculate it using SOHCAHTOA. Then we add it to 90 degrees, which is this remaining part. This is 90 degrees. So this is the reason why the diagrams are important sometimes in solving for polar forms of complex numbers. So we've gotten this. Now we're going to solve this. So tan, I'll quickly erase this a bit. Okay. So tan alpha is going to be opposite over adjacent. We know the opposite is 5, the adjacent is 5, this gives us 1. So alpha is going to be tan inverse of 1, which gives us 45 degrees. Now remember, this is not our argument. Remember what we said here. Our argument theta is equal to, from this our diagram, alpha plus 90 degrees. So this gives us 45 degrees plus 90 degrees, which gives us 135 degrees. So we've simply gotten our alpha. Now our polar form is just going to be, we said our theta is 135 degrees. So our polar form is going to be z is equal to 5 root 2 cos 135 degree plus 5 root 2i sine 135 degrees. You can also factorize it out. You have 5 root 2 into brackets cos 135 degree plus I sine 135 degrees. So if you use your calculator to press this, to try to evaluate this, you're going to get back -5, and if you try this, you're going to get 5i. So that's just it for this example. So we'll take another example, example 3. So for example 3, let's say we're asked to solve negative root 6 minus root 2i. As usual, our x is going to be negative root 6. Our y is going to be negative root 2. Please take note of the signs. The signs before the number belongs to the number. You understand? The sign on the left hand side of the number belongs to the number. So we're going to apply the same principle, everything similar. So let's start with r. R gives you the square root of negative root 6 all squared plus negative root 2 all squared. This gives you the square root of, this gives you the square root. Now remember what we said. We said that when a negative sign is inside an even power, the negative sign disappears. So this is going to give us 6 plus 2, which gives us the square root of 8. This gives us 2 root 2. When you convert to sword, you have this as root of 4 times 2, which can eventually translate to square root of 4 times square root of 2. Square root of 4 gives you 2 times root 2, which gives you 2 root 2. So we've gotten our r. Now our r is 2 root 2. Now we'll go back to our argument. We have to plot a little graph to try to understand the angle. So we have our arguments. We have a line. Okay. Let's adjust this a bit to the left hand side. We have another line here. I have another line. Yeah. So this time around, we have our x to be negative root 6, and we have our y to be negative root 2. So it's obvious that this is the positive y, the positive x, the negative y, and the negative x. The negative x, now for x, it's going to be negative, so it's definitely going to be on the left hand side. So remember what I said, you don't need to include the minus, just write root 6. Now for the y, it's not going to be on the upside, it's going to be on the downside rather, because it's negative. So we'll have, let's say, root 2. Don't include the negative sign. So we'll draw this to the downside, trace this to the downside. Also trace this to the right side, and we connect the two dots. Now this is automatically your r. Yo, just messed up this stuff. Yeah, we can manage this. Yeah, so as we said at the beginning of the video, your arguments always start from the positive x and move until you get to. We're going to start from this point. We're going to move until we get to our r. So this is our argument theta. Now we're going to apply the same principle we said. We know that this is 90 degrees. We know that this is 90 degrees, straight line 180. But we don't know what this little part is. So we're going to call this alpha. So we're going to try to solve for alpha to see what it's going to give us. So we can quickly erase this. So we're going to have like a kind of triangle, a right angle triangle, where this is r, as you can see. This is your alpha. Now, obviously, now don't mess this up. This is your origin, right? So from this point to this point, this is root 6, means that the distance between here and here is going to be root 6. So we'll have root 6. Now for this 2, the distance between this 0 and root 2 is going to be root 2. Same thing applies to this point. This place is the same with this place. So we're going to have root 2 here. Applying SOHCAHTOA also, we have tan alpha is equal to opposite over adjacent. And the opposite is the side the angle is facing, this way. So this is going to be the square root of 2 over the square root of 6. Solving this, we have square root of 2 over 6. So we know that tan alpha gives us 1 over root 3. Now looking for alpha is going to be the tan inverse of 1 over root 3. And alpha gives us 30 degrees. This is a special angle. Now remember what we said, that this is not our argument. So our argument theta is equal to alpha plus 180 degrees. We got 180 from this. So our argument is going to be 30 degrees plus 180 degrees. Argument gives us 210 degrees. So simply go back to this. We have theta as 210 degrees. So Z is equal to, using the formula, r cos theta plus ri sin theta. This is going to be 2 root 2 cos 210 degrees plus 2 root 2i sine 210 degrees. You can also factorize this. 2 root 2 into brackets cos 210 degrees plus I sine 210 degrees. So as usual, if you use the calculator on this, you get back your initial question. I'll go to the last example. Example number 4. What if you have a complex number that is like this, negative 5i? Now, this is a complex number without a real part. What does it mean? It means you can express this as 0 minus 5i. So, still same thing applies. Just follow the same procedure, nothing will change. X is equal to 0 and y is equal to negative 5. The r is going to be the square root of, remember, x squared plus y squared. This gives you the square root of 0 squared plus 5, okay, plus negative 5 squared. This gives you square root of 0 plus, remember, the negative sign will disappear because of the even power. So I have 25. This gives us the square root of 25, which is what? 5. So it's safe to say that r is equal to 5. Now we go over to the augment part of it. And the augment is this. We have this and we have this. Yeah, we have this and this. So remember that this is your positive y, positive x, negative x, and your negative y. So as we said in the according to the question, x is equal to 0 and y is equal to negative 5. So this is what's going to happen here. Your x is going to be 0, meaning that it's going to be at this point. This is one of those special cases. Your y is going to be negative, so it's going to rest along any of these points. So your r is going to be drawn from this origin down to this point. This is your r. Yeah, that's your r. So this is one of those cases where the modulus rests on one of the planes. Understand? So obviously the angle here is going to be, the augment is going to be 270 degrees. So this doesn't need any application of SOHCAHTOA. So we already know that your r is 5 degrees and your theta, your augment, is 270 degrees. So your polar form is going to be 5 cos 270 degrees plus 5i sine 270 degrees. Or you can simply factorize 270 degrees. Now we're meant to stop here, but let's take one more example of one of these special cases. Let's say you have um, let's say you have let's say you have 4i. I'm going to convert this to polar form. Same thing applies. We have 0 plus 4i. We say let the real part be equal to 0 and the imaginary part be equal to 4. We say let r be equal to the square root of x squared plus y squared. This gives you the square root of 0 squared plus 4 squared. This gives you the square root of 0 plus 16. R is equal to the square root of 16 and r is equal to 4. Very straightforward. Now we go over to the arguments part of it. We have, you draw your plane, simply draw your plane. Just simply draw your plane. Draw this. Now, as we said, this is your positive y, positive y, positive x, your negative y, and your negative x. Now, we said that our x is equal to 0 and our y is equal to 4. So we're going to try to plot this. Now your x is equal to 0. It's going to be at the origin. Your y is equal to 4. Is obviously not going to be at the base. It's going to be at the top. So I have 4. Now we're going to connect these dots. And this is your modulus. This is your modulus r. So obviously the angle between positive x and r is going to be 90 degrees. The argument is 90 degrees. So in order to finish this up, your argument theta is 90 degrees. So your complex number is going to be 4 cos 90 degrees plus 4i sine 90 degrees. You can also factorize this to be cos 90 degrees plus I sine 90 degrees. So yeah, the same thing will work if you're given a question of let's say convert 16 to polar form. What you're going to do is just this. You're going to have, now this kind of question is going to be 16 plus 0i. Understand? It means he has no imaginary part. So you apply the same principle. This is one of these special cases. But let's say you have negative 16. It's going to be negative 16 plus 0i. Apply the same principles and you get your answer. So this is basically all about the polar form of a complex number, how to convert from the general form to the polar form.